from continuous seismic data with machine learning approach. So in this talk, I want to convince you that even with one station and a simple method, we can squeeze the data and extract as much as possible information from this seismic data. So I will, for the motivation, okay, so the subduction zones usually have a high seismic hazard region, and usually we have a diversity of the sensor in this region. So we have, for example, broadband stations and ground motion strong ground motion data stations, and also satellite data as well as GPS to monitor this region. And because of these dense networks that we have, usually we have a continuous data streams which lead to a high volume of data. And in this region, because it's very active, usually we have a diversity of the signal in our data. So we want to see how we can extract this signal from our data. In my title, it was about the pattern in continuous seismic signals. So an example of this pattern, for example, is it shows itself in the catalog of the Ridgecrest earthquake. So this is a catalog from 2009 until 2019, before the start of the sequence, with a different method based on it's based on the paper of the Eric Boué. And if we take a look at only a few months of the data before the start of the sequence, we can see that there's an acceleration in number of events. And the other pattern, it can be in the subduction zone, for example, here in Guerrero in Mexico. So we have a earthquake here, for example, or here, and then we have a this is the GPS data, and this sudden change here, it shows the earthquake, and then we have some pattern which take a long time, and this pattern known as a slow sleep event, which is the release of the stress during a long period of time. And usually we have this the signal of this event in our data, which is hidden in our data. And until now, the most recognized signals, so the fast earthquake, which is the signal, we know it, and we have a slow earthquake. So it will start from LFE, low frequency earthquake, which is hidden in the tremors in the data, usually in subduction zone, and then we have a low frequency earthquake and a slow sleep event. And if we look at the scaling law for earthquake, for fast and slow earthquake, so basically here it's it shows the log of seismic moment. Here is moment magnitude, and y-axis show the log of the characteristic duration. So this line is our regular earthquake that we have, and this region is related to the slow earthquake. So we have a LFE here, very low LFE, and then we have a slow sleep event. So it's kind of a discrete. So we want to know, and there also we have a gap between a slow earthquake and regular earthquake. So we want to see if we miss something in our data, or can we automate the process of detecting this event in our data. And it's not only just about localized image signals or events, we can also look for other signatures. So basically, there was a talk with Laurent and also Marin that they showed this figure. So we have a noise waveform, and we can use this noise waveform to monitor the subsurface material. And Laurent in 2008 showed that there is a change in the velocity after Parkfield earthquake. And they show that these changes in velocity is correlated with displacement and also with the tremor rate, which is related to the post-seismic relaxation after the earthquake. And for searching for this event, we also face with, in recent years, we face with the exponential growth of the seismic data. So we have every year we have a more station, and this station exponentially increase. And beside this, new technology also can bring lots of data. And for example, here is the acoustic sensing data. And for 10 seconds of the data and around 300 channel, this data is about 30 megabyte. So consider that we have it for 1 week or several years. So how we can find pattern in seismic data or between seismic and geodetic data that we have? So one way is to use a deep learning or machine learning approach, which can be considered as a two method. One is a supervised learning, which we approximate a function between our samples and the label that we have. So in the supervised learning, usually we require label, some prior information about the data. And this prior information, this label, usually it's limited to known classes. And the other one is unsupervised learning, which kind of approximate from approximate function from the samples that we have or the data and the reconstructed data, or tries to group the data that we have. The good thing about this unsupervised learning is that we don't need a label, but the classes is very implicit that we have. If we want to group the data, which is called clustering, so there is two general approach. One is a top-down approach, which we have a heterogeneous population of the data, and then we try to group this data to homogeneous subgroup. So one of the well-known approach is K-mean. And the other one is the bottom-to-up approach, which try to find groups based on some groups of the data based on some criteria. If we apply this approach on the data, we will get it will work. So we will get some results. So we can cluster the data. But the results will depend on the definition that we use, the method that we use, which is suitable for the data or not. And okay, now let's look at these two waveforms. These two are quite similar to each other. So if we want to group these two, should we put these two waveforms together or not? But if we calculate the correlation coefficient between these two waveforms, we can see it's around 30%. So a slight difference in the waveform can change the correlation coefficient between them. So these changes can be related to amplitude difference, the deformation in the signal, or the overlapping with other event, or the level of noise, or change in the instrument, or change in the media. So how we can extract feature which is invariant in the data. And one way is to use convolutional neural network. So basically, we have a different layer, and we train the network to and extract. We train some filter and to extract feature from the data. And if we look at this feature, for example, these features are related to the first layer in our network. We can see the shape of this feature here. And if we compare this feature with the wavelet transform that we have here, the Gabor wavelet, it's quite similar. So the wavelet and the filters are very similar to each other. So the question is that why we should learn this feature. And instead of learning the network, we just use the Gabor wavelets. And in 2014, Anden and Malla, they propose a deep convolutional wavelet transform called a scattering network. So basically, we have a waveform, we have a signal here, and we apply wavelet transform on it and calculate the absolute value of the output, which is the white circle. And after that, we apply some Fooling functions. So some low frequency, some low pass filter on the coefficients and extract information from the network. And we do it for several wavelets. This is our first layer. And we do it again, applying the wavelet transform on the absolute value of the signal and the wavelet transform. So we take 2 times wavelet transform from the signal in the second layer, and again extract some information from it. So this kind of method is very interpretable because we know what is our kernel in the network, and it's very straightforward to design it, and it can work with a small data set. And actually, the performance is a state of the art for the audio processing and audio classification. So again, how it's work, here I can explain it better. So we have a seismic signal here. And here we have a set of wavelet transform. We call it wavelet band. And we apply this wavelet on our signal. We calculate the scaleogram of the signal. And after that, we apply some pooling function on it. So it's kind of it can be, the pooling function can be average pooling function or max pooling function. It's depends to our application. And we go to the second layer. So we take one frequency of the scaleogram, and again, we apply wavelet transform on it and calculate the scaleogram. We do it for each frequency, and after that, we apply pooling function on it and extract a scattering coefficient from it. So basically, the first layer, it gives us some information about the amplitude of the spectrogram, and the second one, it gives us some information about the modulation of the signal and the shape of the signal, how it behaves. So for applying this method in continuous time series, we have a 3-component continuous seismic signal here, and we calculate the scattering coefficient. So here is our signal. We take a window of we select a window of this signal. We apply a scattering. We calculate the scattering coefficient, and we concatenate it for all of the components. So east, north, and z component. And after that, we apply dimensionality reduction on this, because this coefficient is in the high dimensional space, and we bring it to we extract some feature from this coefficient. And after that, we use this feature that we extract from the scattering coefficient and cluster them. We use hierarchical clustering to cluster this feature. Now we come back to the Mexico. So we have a station here in Guerrero subduction zone, ARIG, which is here is the waveforms from 2009 until 2019. Then we have also GPS data here, SAYA. And here is the displacement in this station. So we have four earthquake, large earthquake in this area. And we want to see that if we can find a pattern, joint pattern in the seismic and geodic data. So we applied the scattering transformation on this data. We used 3 minutes of the window length of the 3 minutes, and then we extract the scattering coefficient from this data, and after that we use independent component analysis to reduce this scattering coefficient to 20 dimension, and after that we cluster it based on the by hierarchical clustering. And here is the results of the independent component analysis. So we have a 20 feature here, and with this 20 feature we could explain the variance of the data, so around 95%. And you can see some pattern in this feature. For example, here there is some seasonal pattern, and in this one we have some localized pattern, and this one is transient, you can see, and this one is episodic. So a lot. And if we apply hierarchical clustering on this feature, we can extract, we can cluster the data, and here is the clustering. So basically, this shows the dendrogram of the data, the relationship between each cluster. So it starts from here. At first, separate this cluster, and then goes for these and these four, and then this. So this cluster is usually related to the quality of data. And if we go to the waveform, we can see these are the waveforms related to this cluster. And here in this plot, it shows the detection rate over time. So basically, it shows the detection rate, and then here we have a distribution of over day, and in the end we have a population of each cluster. And if we look at this cluster, for example, cluster, I'm not going to interpret all of these, but some of them. For example, cluster L2 is related to the seismic, to the local earthquake, and cluster I is related to the tremors. And here you can see better the waveforms that extract. Here is the cluster L2, which is related to the local event. Cluster K1 is also related, and cluster I is related to the tremor that we in cluster I. And yeah, if here is an example of one of these tremor in the cluster I. So here you can see the waveforms for the different component, for the east component, north, and Z. And here is the scattering coefficient, the average of the scattering coefficient for this cluster. So this is kind of shows the amplitude of the first layer, and this one shows the modulation for each frequency. So for each frequency, we have a modulation in the second layer. And if we use if we calculate the cumulative number of the event in the cluster which is related to tremor, cluster I, and compare it with the tremor catalog with Hasker, we can see that we could kind of capture the shape of the catalog, and also we could detect a higher number of the events in this cluster. Now we have our detection rate for each of the cluster, and also we have a GPS data, and we want to see what is the contribution of each of these cluster in the displacement rate. So we want to kind of decompose this GPS data on this different cluster that we have, seismic cluster. And for this, we use a linear regression problem. So basically, we try to estimate a coefficient, which is the for each of this cluster. We try to estimate the coefficient that can reconstruct the data. And if we use linear regression and apply it in this data here, we could, with this seismic cluster, we could reconstruct 95% of the GPS data. And here you can see that the displacement rate per waveform is about minus 1.5 for cluster I, which is related to the tremor. And also we have for the earthquake. For the earthquake, cluster L2 also is related to, is about -2. And also we have, for the cluster J3 also, there is some displacement rate per window. Now we go to Ridgecrest earthquake. So Bose in 2024, he used several seismic stations, and he applied template matching and pack propagation method to detect a seismic event in this region. And he used several stations. So you can see that before the Ridgecrest earthquake, there was an acceleration in the number of events. And we used only this station, B918, and we want to see if we can, only with this station, we can capture this acceleration or not. And here is the result of our clustering. Again, here is the dendrogram, which shows the relation between our different clusters. And here it shows the detection rate over time and the distribution over day. So cluster 8 is mainly anthropological noise that we have, which occur during the day. And cluster D here, it's mainly related to the earthquake. So Sarah, she has a poster on it, which you can see. And we only use these two clusters, D1 and D2, and calculate the cumulative number of the event. And we show that we can capture the acceleration over time. But not the number of the event is not, we detect less event than in the catalog. So now we come to Russia from California and Mexico. And in the Kamchatka, there is a volcano here, very active volcano. And we have several stations in this region. So the nearest station to the volcano is 5 kilometers. And during 2015 and 2016, there was an eruption here. Basically, here you can see the detection of the tremor over time. based on depth. And here you can see the daily activity level for this time period. So basically, the green is a low volcanic activity, red is medium, and then it's become ongoing eruption, and then we have an explosion. And also, the dot here shows the satellite data, which is the result of the satellite data that they use to calculate the lava discharge rate over time. So you can see that there is actually increase of the discharge rate here. And we want to see if we can see any pattern in the continuous seismic data for this region. So we have a continuous seismic data. We calculate a scattering coefficient. And then instead of cluster the data, go to use a low dimension, reduce the dimensionality and cluster the data. We use the UMAP, uniform manifold approximation and projection. So basically, we reduce the dimension to 2 for the visualization. And the method is work based by capturing the local structure in the data. And you can see the result for the MNIST data based on the different methods. So based on the PCA, which captured the two largest variants in the data, and the UMAP, which you can see that the method can better localize the different clusters. Yes. MNIST is the data in, it's the written number in the machine learning community that usually they use it for the validating the method. No, it's not a volcano. It just showed that how it's work. And if we apply this here, apply this UMAP on the data, on the scattering coefficient, it shows the here, what you can see is the result of the UMAP for different stations. So it's in the 5 kilometer station, which is in the distance of 5 kilometer, 30 kilometer, and 100 kilometer. And the color code here, it shows the time. So here is the start of the data, and the red one is the in the August, the explosion. And you can see that how it changed with the distance. The data changed with the distance. So here we can see that the dynamic of the data, usually we have more signals in the data that could capture, separate it from each other. And when we go far from the volcano, it's just grouped together. And if we instead of the time, we use discharge rate of magma, so lava. So we can see here, basically here is the nearest station to the volcano. And you can see that in this area, we have a lowest amount of the discharge rate. And then in this area, it's increased. But but for farthest station, there is only a group of it's grouped together. And the interesting thing is this figure, which is show the dynamic of the volcano for the station near to the volcano. So basically, it starts from here. So here is August 2015, the first of all, that we have some deep tremor in the data. We are here. Then we have some weak signals or noise in this region. And then after a while, we have some reactivation. So it starts from some strong, deep reactivation in the volcano. and after that, we have some deeper tremor. We have some shallow tremor here. And then again, we go to the deeper tremor. And after that, it's become here. So here is the mostly shallow tremor that we have. And then it's become, again, weak signal and noise. So it's become to the very close to the state of 2 that we had. And after a while, again, we have a deep reactivation in our data, in the volcano. And then we have a pre-eruption shallow tremor. And after that, here, there is a deep tremor before the eruption. And then eruption starts here. And after that, this red pass here, it shows the deep tremor that co-erupted that we have here. And then we have again co-eruption, random tremor in this region, and then it goes to the seismic intensification before the explosion. And then we have explosion here in this region. So this is another work that we start to use this scattering transformation for it. So we start with the we want to see if we can characterize the highly heterogeneous media based on the synthetic data. So we have a receiver in the surface, and we have a source in the media. So we can act as a scattering, and it's around 5,800 sources with a regular grid and 5 stations in the surface. And here it showed the result of the 2 sections that we have. One is for 20, and the other is for 85 in this region. And it showed that for the low velocity zone, we have more Coda wave in our data in this area. And we want to see if only based on this scattering coefficient extract from this seismogram and the UMAP atlas, we can capture this low velocity zone in the media. And for this, we use UMAP. Here you can see. So here is the first component and the second component. The colors show the velocity in the medium. And if we localize this, and then what we did is that for each of these points, we calculate the number of the component that can explain 80% of the variance in the database by using PCA. And if we localize these values in the UMAP, in the subsurface, in the medium, we can reach to this plot, which is very similar, kind of similar to our velocity model that we have. This is kind of still in progress. I just wanted to show you this result. And in the end, in the end, this scattering transformation and this method can be used for the clustering continuous seismic data that we have. It's very straightforward to design this network and interpret it. And it can be used for the single station at the moment. But our perspective is that extended this method to the multiple station. And after that also from multi-event, allow for multi-event per event. And then we kind of use the inverse transform of this scattering transformation to come back from each cluster to the time domain and see what's happened in the time domain. And also here is the package that we use for our work. Yeah, thank you so much.